So my name is Jeff Buterbaugh. I'm with Conrad Technologies. I've been there the last 6 years. I'll give you a little intro to Conrad in a moment. For the 20 years prior to that, I worked for NI in a variety of roles. I live in Columbus, Ohio, so I started off as the NI guy for the Ohio and Kentucky in the late 90s, I guess that was. And then moved into a business development role for sound vibration and predictive maintenance and machine vision across the Midwest, and met some of you guys in that time period. And then I became an account manager around 2010 when then I started focusing on some of the larger accounts. And I worked with GE Healthcare, was one of my accounts. So it's good to get back there earlier today. And then eventually ended up working with some automotive accounts. And as part of that, ended up deciding to come to Conrad. And that's where I've been the last 6 years. So it's been a 26-year run so far. And in case you're wondering if there happen to be just accidentally two people in the room with the last name Buterbaugh, no, that Preston is my son back there. So, all right. Okay. So Conrad is a global NI Alliance partner. Been around a long time, since 1993, founded by Michael Conrad, who is still our CEO. 2017, largely based on some of the success that Conrad was having in automated driver assistance testing and other automotive applications. They felt like they needed to have a U.S. presence that was larger than the very small footprint they had at the time. So they acquired another NI Alliance member, VI Engineering, based just outside of Detroit, Farmington Hills. We have about 300 global employees. The U.S. headquarters, as I mentioned, is in our Detroit office. We also have an Indianapolis office, and a few of us kind of randomly scattered around. About 50 of us in the United States. We also manage a team of about 25 in India, out of the U.S. office. Most of those folks are engineers. About 4,000 square feet of shop space in Farmington Hills, and that's where we will build the custom turnkey test systems that is our kind of our primary business. We also do system retrofits and upgrades, engineering information management. That's code words for like system link, diadem, and we have a product called Test Valet that falls into that category. Just anything associated with kind of the business or data management side of test. And then we have a model called Flex IPT, which is our flexible integrated project team. Which basically we become an extension of our customers' project teams by giving them a consistent project manager and tech lead. And then they can come to us at any time that they need help with their LabVIEW or their design or their build. And we'll work with them on a time materials basis at a pre-negotiated set of rates. And they can just spin that up and spin that down as whatever they want. And we will, there's basically zero start time, and we always give them the same project manager and tech lead they had last time, so they don't have to reintroduce themselves and such. So anyway, I kind of gave you the timeline of VI and Conrad, but what used to be VI Engineering, like 98% of us are still there. We are the U.S. or America's headquarters for Conrad. We work very closely with NI. We also work with a lot of additional partners. Many of you who are NI customers are probably represented by Mark Smith at TestForce. We work very closely with TestForce. We also work with Pickering whenever their switches need to be involved. eSite, when their instruments make sense, we're aligned with them, for example, on like EV charge port testing applications. But fundamentally, we are an NI house. So we have lots of certified developers, certified architects, as well as test and certified developers and architects. I need to get rid of my little. Customers say nice things about us. That's Not surprising, probably. Okay. And then there's basically two of us that cover the Americas. Some of you may recognize my colleague, Joe DeRosier. He just joined Conrad in the earlier this year, but previously he was an account manager for Averna, another Alliance member. Prior to that, he was an RF business development manager and sales guy for NI as well. All right, so I'm gonna spend my time today talking about battery cell quality test. Before I do that, just so I can kind of gauge the level at which I should put this conversation, how many of you guys are already doing battery testing? One, two. All right, good. All right. Can you just give me some background on like what kind of battery testing you're currently doing?
It's battery management systems.
EMS.
Okay. Actually cells.
Okay. All right.
Pack level testing.
Sorry.
Pack level.
Pack level test. All right, you go pack and module. Okay. All right. So this will be different, or pack and BMS. So this will be different. Okay. All right. So I'll keep it more at the intro level, but I've got detail slides. If people want to go into the weeds, we can. I'm not promising to just be the expert on all this stuff, but I did kind of geek out on this when we got into this area of testing. My PhD from way a long time ago is in analytical chemistry, and like all those electrochemistry classes I thought were irrelevant are now suddenly relevant again. So it's a little bit fun. All right, so batteries are everywhere. I hopefully don't need to tell anyone that. They are in every aspect of engineering, product development, products everywhere, whether it's consumer product, medical device, transportation, mil-aero, anywhere that's using NI, LabVIEW probably. There are some devices that have batteries in them, and the battery lives are important. The battery safety is important. All kinds of things about the battery are important. So the cell production process is under constant pressure to be improved because the scale is increasing, yet the demand to be profitable is also becoming more and more important, and especially in the EV market. And yet, of course, quality is critical because nobody wants their product on the nightly news in flames, causing a problem somewhere. So it's an issue. So at the module and pack level, there are, cells are assembled into sub-assemblies, which are then further put into a pack. NI obviously gets involved in those tests as well. Service and manufacturing is important too. I'll show you an application later where we're doing reconditioning of batteries. One of our customers is, and we're helping them test qualify the reconditioning. But if we look specifically at the cell manufacturing process, this is the individual level of the electrochemistry. The production time for an electrochemical cell is typically 8 to 10, 12 days, and yet the scale is huge. There's a lot of variability that creeps into these processes that end up having sometimes poorly understood impact on the cell yields. Some of the defects can be very difficult to identify, and so it's kind of a hit or miss. Whether you're going to have a yield in some cases, it becomes very hard to determine root cause, and so there's a strong demand in the market to improve the information content of battery testing. Not just is it above or below a certain voltage threshold, or is it generating the right amount of current for the stated period of time. People want to go kind of beyond the typical spec sheets to figure out, is there anything that we can look at early in the life of this cell that will inform us as to whether we should just stop manufacturing that particular cell or pull it out of circulation because we've learned something about a root cause issue that is going to cause it to have a more likely to have failure down the road. And these could be all kinds of failure modes. This is not intended to be a exhaustive list, but obviously if you have wrinkles or folds in the casing or in the separators, if you have dendrites building up torn weld tabs, anything like that is going to create a hot spot in the battery and a potential area of short circuit or failure. Typical cell manufacturing process includes a number of different stations. The cells may be parked in any of these stations for particular different periods of time. And so the testing is going to show up at various points in the process. And the different tests are going to be relevant at different points in the process. And so, again, we're going to focus on cell stuff today, cell quality in particular. This is basically verifying the battery cells, usually in a qual environment, like at your supplier qualification lab. If you're sourcing your batteries from multiple vendors, for example, many of them are coming overseas. You want to do spot checks, in some cases 100% checks, but usually spot checks on each batch of cells to make sure that they meet your standards. This is an extremely common use case. And again, depending on what industry you're in, becomes more and more important. I've got a couple of medical devices pictured on the screen because those are devices where I think we all understand a failure in a battery on a medical device is a significant challenge. Maybe more particularly so in an implantable, but you don't want to be diving into somebody again to go get a battery. Very uncomfortable. So obviously, this is an NI slide. It's a commercial for NI PXI. I'm going to guess 99% of you here have already seen some slide that looks a lot like this before. But the main point here is that all of the benefits of software-defined instrumentation and the PXI modular instrumentation platform that we've all come to know and love apply in spades to testing battery cell quality. All of the channel count flexibility, all of the ability to combine different instruments in new and innovative ways, the ability to apply software algorithms in new and creative ways, to use post-processing tools, maybe after the test, you want to do some statistical process control or other metrics on the system that Chris Nelson back there would probably like to talk to you about. All of those apply to battery cell quality because you're dealing with very high channels, high channel counts in many cases, high number of just total volume of tests, and poorly understood data. So that just lends itself to D&M and data mining and machine learning, AI, all that fun stuff. So all the things you've come to know and love about NI certainly apply here, and that's why NI is actively going after this market, and that's why Conrad is very eager to pursue these opportunities. The NI cell quality toolkit, I don't know if that's the final name of it or whatever, is slated for official release sometime here in the next 2 to 3 months. We've got pre-release deployments of it already. So you don't need to necessarily wait on the official toolkit to be supported by NI to leverage it. But the 3 measurements that are going to be supported right out of the box are open circuit voltage, ACIR, and EIS. And we're going to talk about what all those things are. But basically, for those of you guys just like to boil things down, we're looking at a DMM and an SMU, source measuring unit. Those are the 2 instruments. So all the fun stuff is in the virtual instrumentation. All right, so what does Conrad have in this space? This is not, strictly speaking, using the cell quality toolkit, but this is a project we did several years ago. We've actually sold it to 2 different medical device customers so far. It's a constant current discharge tester based on PXI for button cell coin cell batteries. These are both of our customers that we've had so far in the medical device industry. This fixture holds up to 100 button cell batteries, and the clamshell just closes down, and we start testing all 100 of them in a constant current discharge environment. So we're measuring the usable capacity of the batteries at a specified discharge rate. So this is something we have available right now. Open circuit voltage is just, as it says, the open circuit voltage potential difference between the terminals of a battery cell when there's no load connected. Okay, so this is something that is typically a very quick test done with a DMM. You can obviously measure very precisely with a DMM. But the key technical challenge is not a major challenge, but it's one that you only want to connect to the circuit when you're making the measurement. Otherwise, it won't be an open circuit voltage. You'll now be applying a load. And so you don't want to do that. So the basic goal is to connect to the cell periodically over a long period of time and make these measurements. And so usually you're just checking to see if it's at what point the leakage current in the device has basically dropped your OCV below its threshold value. And it can sometimes be used as a proxy for a state of charge. It's very sensitive to temperature, so it's always good to measure this in conjunction with temperature. In fact, most of the systems that I've seen are actually doing these in environmental chambers and controlling temperature, either at a profile or more commonly, they're just soaking at a particular temperature. So, the goal here is just to detect the magnitude that always exists of these micro shorts during the cell aging process. And so you monitor the variation in open circuit voltage. In manufacturing, what you'll see is that all the good batteries will have curves that match, one similar to the one on the top. The less performant batteries will usually fairly drastically dip below that, and that'll tell you that there's something, critically wrong with that cell. So in a manufacturing context, that's how it's used. In the validation process or just the design process, it's more that context I just mentioned, where you'd be in a thermal chamber, you'd be looking at these over days, weeks, months, years, and checking in on a periodic basis. Okay, so depending on the instrumentation you choose here, you can get extremely precise measurements. You can measure up to a kilovolt on an NI platform. You can go beyond that if you need to. Might want to stand far away from your system if you do, but there are other instruments available that will do that. But the NI platform is great for this. This is just if you see there's this traveling NI cell quality demo that maybe NI is brought to a theater near you, but if you go to a trade show, you'll definitely see it. It'll be at Automotive Texting Expo in November, October, if you want to look at it there. But this is what their demo of that looks like. But more interesting to me is that Conrad has deployed for a major OEM in the Detroit area. I think about a dozen of these cesters that are exactly what I just described. They are inside each of these racks is a PXI chassis with a DMM and switch matrix. And there's these honking huge cables that come out from the back of this that are distributed out to one or two thermal chambers. There's a connection to every single cell, prismatic or pouch cell sitting in the thermal chambers. We're measuring the temperature and we're measuring just to check on the thermal chamber. Obviously, the thermal chamber is supposed to be controlling temperature. We do a sanity check to make sure it's controlling it at the correct temperature. And then we're also, once a day, we connect for 10 seconds and do 10 samples, average them, and then disconnect. It's like the world's most boring measurement, but it's very important to the customer. And, we have a very nice solution for it. This the monitor, we got a really cool LabVIEW GUI that's got their logo and it's got all the little battery cells and they're like, percent charged thing on each one of them. It's pretty slick. All right. Now let's get into the more interesting measurements. AC internal resistance. This is measures the resistance to alternating current flow within a battery cell. It's typically used in the manufacturing process at the finishing stage, cell finishing. Here we are going to actually use an SMU to apply an AC waveform to the cell, and then we're detecting then the resistive and reactive components of the returned signal. Okay, so here we've got a multiplex switch if we're doing multiple channels, but basically it's just often a SMU per channel. This is a pretty quick measurement by definition. ACIR is done at 1 kilohertz excitation, and so this data I think takes a few seconds to acquire. Again, you're typically going to see a fairly consistent value for ACIR of your good cells, and then you're going to see a distribution where the ones on the periphery might be suspect in some way, shape, or form. But it's still fundamentally just a single point measurement. And so that obviously doesn't have a ton of information content built into it. But again, it's resistance to alternating current flow within a battery. It's done in milliseconds to seconds, more efficient than DCIR, which I'm not going to talk about tonight. But that's just DC stimulus and measuring the internal resistance, which requires a longer observation while you're applying DC load. And ACIR is influenced by the cell chemistry, the electromaterials, and the electrolyte properties. Okay, so what we use ACIR for is typically as a prelude to an EIS measurement, which we're going to talk about in a minute. But usually you would have a threshold ACIR value or a threshold OCV value that you're looking for to decide whether a cell is even worth further testing, because you can finish that measurement very quickly. Okay, if either the ACIR value or the OCV value is out of spec, then you fail the part. All right, so obviously very fast. ACIR can be done early in cell formation, so you can often catch problems quickly and just not bother to add any more value to that cell. So that's the main goal of that.
So what parameter do you use then? Is it the magnitude? I mean, it's a complex waveform. You look at the
it's the frequency response. Oh, hold on. I thought I had it's the complex impedance as a function of reactance at that frequency. I need to go back to my mathematics books to tell you more about what that means. But it is a
The chart
it's
is
a
too, it's
point
real
of
imaginary.
real imaginary part of the impedance, right? Okay. Oh, sorry. Thank you. That is real and imaginary. Thank you.
So the cell is both charging and discharging during that time.
Yes, because you're pushing current into it and then watching the decay. It's like it's a pulse event.
Do you do that to both, well, I guess I'll say single-use batteries and rechargeable batteries? Or are these all rechargeable?
I've not seen it done on primary cells.
Okay.
It's always been the rechargeables that we've been involved in. I don't know if that has to do with the value of the DUT, right? I mean, if you get a bad cell battery, I'm not sure the consequences are as bad as if you have one in a rechargeable context, but I'm not sure.
Yep.
Okay, so the most interesting in my mind, and in most people's mind, part of battery cell quality is electrochemical impedance spectroscopy. This is also where the NI platform has most of its differentiated capability. And so I'm going to spend more time talking about that. EIS provides detailed information about cell behavior across a range of frequencies, including information on charge transfer resistance, the diffusion processes that might be occurring within the cell, and capacitance. And so here we're going to measure that impedance that we were measuring in the ACIR, but now rather than just using the 1 kilohertz excitation, we're going to sweep through a whole range of frequencies, usually logarithmically spaced frequency values to create a spectrum. That's why it's called an electrochemical impedance spectroscopy. And so here, the current NI tools will support up to a kilohertz of AC excitation. I think that very soon after that, they'll support beyond that, just by qualifying different SMUs and so forth for the process. But the benefit here is it's relative to the other instruments on the market that do this measurement. The NI instrumentation is extremely fast. And then where the NI instrumentation really comes into another major value it has, just by the nature of modular instrumentation in PXI, if you need more than one channel of this measurement, then the cost per channel is quite low because you really just need to add a new SMU channel for each system you want to bring in parallel. You can share the PXI chassis, you can share the software, you can share the footprint. So it becomes much more cost effective. Okay, so this is the block diagram here. Again, you can do EIS up to 2 megahertz on other platforms, and ultimately on the NI platform, that should be possible as well. And you can do up to 2 amp current. So again, the use case for this is typically after you've done the OCV, ACIR, pass fail, you'll select the cells that pass that test to go on for EIS. This is going to give you potentially, okay, the detailed information about charge transfer resistance, diffusion, capacitance, etc. And then you can use those spectra to validate cell quality, identify specific chemical processes occurring in the cell that may or may not be supposed to be happening, and optimize your cell performance. So it's really a much more detailed window into the electrochemistry of the battery cell. And you can even find software models that will create like equivalent circuits for the battery out of your EIS data. This is available on the market from a variety of vendors. I'm guessing that we can get it implemented in LabVIEW soon, or some way to call a third-party tool if that's interesting to a particular customer. We haven't had that request yet, but this is something that's done in industry with EIS data. One other thing about the interpretation of EIS data, and I've got a whole section on this that I won't have time to go into, but it becomes an intersection between art and science at some point, is that there are some things that are kind of like general trends about what you might see in one part of an EIS spectrum or another, but it's really, really specific to the chemistry of the system that you're looking at. And so it's very hard to generalize beyond certain very broad categories of what a particular feature in an EIS spectrum represents. But the good news is for most industrial customers, they're making a bazillion of the exact same cell that's supposed to be the exact same chemistry every time. And so these faults tend to self-identify into various regions, and you can do root cause analysis of some of your failures and then begin to associate certain features in the EIS spectra with certain causes. And of course, again, at the industrial process level, sometimes you don't even care if you're right about the root cause. You're just better safe than sorry. If you see something over here and it's only occurring once out of every 10,000 cells, probably safer to pull that one out of circulation than risk that it might have some problem.
Hey, Jeff.
Yep.
Question. So that's how you characterize your equivalent series resistance and the parasitic capacitance, your parallel capacitance of your battery. Is that what this test tells you?
It tells you a number of things, possibly including those two values. But again, the specific parameters, I mean, it's really, there's nothing intrinsically in there beyond the real and imaginary components of the impedance at different frequency excitations. That's intrinsically what's in there. It gives you insight potentially into the chemistry of what's going on either in various regions of the battery. Again, because they're going to have certain resonances, for lack of a better word, certain slow processes are going to be seen more at the lower scan rates, and certain high frequency things are going to be seen, shorter distance phenomena are going to be seen at the higher frequencies, and so forth. You're going to see shapes in the data, and I might have a couple examples of this here. Very clearly, what you almost always see is a radical difference in the shape of at least a part of the EIS curve based on a cell that's good versus one that's bad, regardless of what good and bad caused good and bad. What is more challenging is assigning root causes to specific shapes, but there are some guidelines. And again, I can show you some of the slides on that if you're interested, in terms of what specific information might be in there. But I think that, at least from what I've read, trying to just come up with a recipe for saying, oh, if you see this in an EIS, it means that, is probably oversimplifying the interpretation. So
for your NIH battery test systems, this is how you kind of categorize your slew rates. If you're doing this type of testing, you just want to have your slew rate a little bit lower, or a little bit longer.
okay, but which test are you talking about specifically?
For for the NIH battery test systems.
NIH, like,
So NI.
is that a standard from the National Institute of Health that you're saying? Is that NIH or what? Or are you talking about NI for NI, like National Instruments? Okay, National Instruments. Okay. So help me understand the question then.
So we're kind of alluding to kind of developing different profiles based on the slew rate, whether it's discharging fast or discharging slowly. And I was wondering if this is kind of what you were alluding to, was more that you were starting to say, if you're under these conditions, this is what slew rate we would recommend you use.
Yeah, so there's a whole bunch of subject domain expertise that I don't have in the full answer to that question. But the basic answer to that question is you will often use EIS early in your investigation of a particular cell type to figure out where the interesting features are. Okay, what if you notice over the course of 1,000 cells that you see some things going on here in the high frequency range, some things going on in a certain low frequency range or whatever, and not a whole lot going on in the middle, then you might configure your future EIS testing to maybe sample more frequencies where you saw problems, and maybe skip faster through the frequencies there where you never saw anything interesting, right? So that would be one way to tune your EIS measurements over time, is as you learn more about the chemistry, either at a fundamental level or even at an empirical level, you can adjust the excitation pulse frequencies in your EIS spectrum. There's no like standard set of frequencies that you use for EIS. It's just, whatever works for your system. So that's something you learn over time about the chemistry of the system. Okay, so this system right here is hot off the press. This is a system that we're delivering to an automotive customer. This is reconditioning EV batteries that have been, returned back for reconditioned use. And so our customer needs to perform this process for their customer. And so they receive the old batteries in-house, and they want to quickly then determine which ones are candidates for further processing. And so this leftmost nest that you see here has, we've developed a pneumatic system to engage the cell in the nest. And the nest is, I believe, 3D printed out of a non-conducting material. So it's very, very safe for the process. And then we're reading a barcode to enter the system, enter this cell into the database. And then we're basically doing a very quick open circuit voltage and ACIR measurement. We're actually using a Hioki instrument for that, only because the customer's customer requires that. That's what they use in Japan. They're going to use it here. So we're taking that measurement using the Hioki instrument. If it passes that test, then the operator is instructed by our software to place the cell into one of the 8 additional nests. And there will be an LED that lights up on the appropriate nest. So the operator puts it in the correct one. There's also, not shown on the screen, some safety stuff here to prevent the operator from doing something they shouldn't. And then we initiate an EIS spectrum for each of these. And I believe that requires a few minutes to run for each test. So we'll basically step through each of the nests. The load will be phase shifted relative to each other. So one operator can operate this station and manage up to 8 EIS spectra occurring at once. The EIS spectra, currently the customer doesn't even know how they're ultimately going to use that data because they don't have any history. But over time, they're going to build up a history of the EIS spectra and learn about what might characterize a cell that's really not suitable for this reconditioning, or they may just end up using it to pair similar cells together in the new pack. Because one thing that's almost always true of pack and module, from my understanding, is you want the cells to be as similar as possible to one another. So even if you don't fully understand like why this one has this little wrinkle in its EIS and this one has a different wrinkle in its EIS, if you find 2 that are the same shape, that is likely to be a better pack than 2 that were different. Okay, that sort of thing. So, I forgot to make an edit here. My technical team told me it was not nylon. It's some other non-conductive 3D print material. So sorry about that. The other thing that we do here is we have a temperature sensor. I believe it's an RTD in each of the nests, because EIS spectra are extremely sensitive to temperature. And so even if you're doing this in ambient room air, it's probably good to have that as a sanity check. Also, you can correct the spectra for temperature over time as well. Okay, so the software architecture for this is there's a main user interface. There's some utility screens that allow the operator to kind of do a zero correction for each of the nests, and also to do temperature corrections to the system. So it's sort of a calibration. There's a whole calibration golden dot that we have that you can use to do the internal calibration of the system. And then the GUI will then call, based on what the operator presses, either an ACIR process to do that initial thresholding, or then it runs up to 8 of the EIS processes in parallel. So those are all independent from one another. And I apologize for the small text here, but we can get you the slides if you're interested. Okay. It's just a couple of examples of the operator screens. Generally, I'm pretty impressed with the Conrad engineers GUIs. We do a lot of, we attend a lot of the LabVIEW forums and so forth, as well as the higher level training classes and certifications. In fact, some of our engineers, I think, even lead some of the NI Connect sessions on user interface design and so forth, and argue with each other about how things should look. But maybe you guys are parts of those arguments. I don't know. But basically here, this operators just being instructed to unload the cell from the ACIR and place it in the next available EIS. You can see that it's passed its OCV and ACIR, and move on. And then this is a screen from the zero adjust screen there. Just a couple of random screenshots. These screenshots are in the 95% completion date. So, some things may not be exactly what the final delivery will look like. This might be hard to read on this particular screen, but if this is a Nyquist plot, a part of the one way of looking at the EIS spectra. You can also look at the magnitude and phase Bode plots is another way of looking at those data. All right. I'm going to skip all the YPXI stuff because I think you guys probably are already sold on PXI. So we'll get into this. Is actually an interesting, let me unhide this one. Just to show you some of the NI demo screens here. The ACIR, as I mentioned earlier, is just the one data point on an EIS spectrum where the sampling is at 1 kilohertz, or the source excitation is 1 kilohertz. You can see that if you just looked at those 4 points, you might not be able to tell a whole lot of difference between the 4 traces. But if you run the 4 EIS spectra, you can see that actually there's quite a bit of difference in those 4 traces, indicating that the one in red is radically different from the other 3. And there might even be some variation of significance among the other 3. It's hard to say. It's a little closer look at them. And just showing again how, the ACIR measurement by itself wouldn't really tell you much, but if you do it over multiple frequencies, you can see how similar plots will line up on top of each other, or similar cells will have their plots line up on top of each other, whereas the others will have different. Okay. All right, so I am going to wrap this up. As I mentioned, let's keep it on time, but I do have slides on the interpretation of EIS data. It's not a recipe. It's just general guidelines. This is not out of my own brain. This is out of, surveying of literature and what's available online and trying to make sense of it and collate it in a way that's intelligible to the masses. But, would appreciate your feedback on it, actually, for any of you guys that do work with battery tests, because it's kind of a work in process. I'm proud of this on my side. Any questions?
So you mentioned ECIR, starts at 1 kilohertz, and then what's the maximum frequency of interest?
ACIR by definition is 1 kilohertz.
Okay.
EIS is any of the arbitrary excitation frequencies. Currently, you can support everything from DC up to 1 kilohertz on the official NI toolkit that will release in 3 months, sometime in the next 3 months. Generally speaking, there are instruments on the market that support up to 2 megahertz of excitation, and the NI instruments can actually do that. It just hasn't been validated by NI yet to be valid. So the instrument will generate data. It's just, is that as precise as it needs to be? Do we know what the threshold tolerance? All that stuff is still to be determined. But the NI instruments are capable of doing the high frequency stuff as well. And it can do it a lot faster than the non-NI solutions. Other questions? Yes.
So I'm pretty unfamiliar with the battery testing on this level, but through the EIS, do you see any noise related issues when testing multiple cells at a time, or anything regarding the EIS?
You absolutely could.
Yeah.
And it just means you haven't built your test fixture well enough yet, is my understanding. From talking to engineers, both at NI and internally, there's a lot of secret sauce, or maybe not so secret, but let's just call it lessons of learned school of hard knocks of how to actually build a nest properly, how to minimize the cable lengths, how to minimize interference among cables. Because yes, you're dealing with very, very low level signals. And when you're doing the high frequency pulses, you're generating potential sources of noise. Yeah, you have to be careful with everything. Yes. So you do. Good question. Yeah, everything in that test system that I just showed you is designed to minimize variability and everything. But in principle, if you keep the cable length short enough and you keep everything isolated enough from one another, there's really no fundamental limit on how many channels you can put in there. Yeah.
Yeah, with your EIS testing and ACIR, are you, what's the, like the set point, like the DC level of the signal? I mean, are you actually reversing current, or are you having a net current draw and you're changing the amount of current draw with that waveform?
That's a great question. I don't know the answer to. I thought it was around 0, but that may not be true. I think you are reversing. Though. I think it does go negative. I will find that out. I need to know the answer.
I think maybe you had a waveform.
Yeah, did I have an actual screen? I don't trust the NI. There's no NI in here. Is there, you know?
I think I had an offset, but it was both charging and discharging.
Yeah, I'm not sure that, depending on who made the slide, it may or may not represent. Might just be a pretty picture. Like there's nothing marked on there. That's not the one you're talking about? Was there a actual waveform?
That might be it. 0 offset.
Does it say that?
Charging, yes. No, but that's what I noticed on that
Oh.
graph.
Can't see that one. No help. Okay, so I'll find out. And
I was wondering on the.
you all have my card, so email me and I'll get back to you.
On that open circuit voltage test, that seems just highly dependent on state of charge that the cell is in.
Yes, absolutely.
Does it first charge it,
Yeah.
then test the.
Right. Absolutely. And it's very limited, but it's useful in like the application I showed you from the automotive OEM is very useful though, because they have a fully charged cell and then they just let it go, right? Over time, they don't connect it to anything. They just let it sit there in the chamber. And over months of time, it will deplete, and that is just due to the self-discharge.
Gotcha.
All right. I need to leave time for Mr. Ridgely if he's the next presenter. Don't want to steal his time. So thank you guys very much. I will be passing out Conrad screwdrivers to those of you who are here in person. Sorry for those of you guys online. I don't have any way to throw one to you.
All right. And you guys can hear me and see the screen, right?
Yes, sir. Yes.
Okay, awesome. Well, first I want to thank you all for letting me speak at your meeting. It's a great opportunity. Good presentation from Jeff on the batteries, and a lot of interesting people in the room. It was good to hear that we have a lot of experienced users as well as some newer users. I'm here to talk about the training aspect of learning to use NI products very well on your own. And I'm Mark Ridgely. I'm going to introduce myself a little bit here, just a few slides, probably 5 minutes at the most, and talk about NI's new authorized training partner program, which Radius Technologies is a part of. So I'm Mark Ridgely. I am an NI authorized training partner for the Midwest region, and I'm the owner of Radius Technologies LLC, and certified in all things LabVIEW, certified instructor for NI. I've been using LabVIEW since version 3 and been teaching it since version 4. So I think some of you guys got a few years on me, even beyond that. But, I've been teaching it for a long time. So that's what I'm here to talk about. Here's my contact info. I'm pretty readily, easily found online on LinkedIn. And then my company website is radius-tek.com. So if you ever want to reach out to me, you should be able to find me easily. This is where I'm located in Minneapolis, Minnesota, not too far from you all, but the region that I'm targeting to cover with the training is the state shown on the slide. So being that this is the only training center in the Midwest, hopefully people that need training and want to travel will come here to Minneapolis and get their training done. And we're located about 5 miles west of downtown Minneapolis in an area that's called the Shops at West End. It's a very nice area with a lot of hotels. This is the building here that we're in, and the area is shown here. So on the upper left part of the picture is where the actual training site is. And then there's multiple hotels, restaurants, all within easy walking distance. So it's a great area. If you're going to be going somewhere for training, this is the place to go. There's a few pictures of the actual training location. So we got a nice, modern, clean facility, and we're going to have some great trainings here and do a good job in doing that. So these are, some of the services that I offer as Radius. We will be proctoring NI certification exams. I know some of you said yours just expired, so I'll be hoping to see you in here soon to get recertified. But other than that, we also do training for NI courses, NI's official courses, and I teach just about every course that LabVIEW has offer. So if you need training and you want to travel and come see Minneapolis, this is the place to go. And these are some reasons that you want to come here for training. It is going to be an elevated training experience, and I'm planning to provide great service and training, great food. You'll be getting catered breakfast and lunch every day. And we're not just talking a box of donuts slammed on a table. These are going to be meals that are curated just for these training things. There's going to be snacks available all day. And we're going to be using the NI course materials. And big plus is you're out of your office, so you're away from your normal daily distractions. So you can really focus on learning. And upcoming courses, we had a LabVIEW Core 1 and Core 2 starting on September 16th. So for you new users out there, if that's something that you might want to put on your calendar and try to attend that, we'd be happy to welcome you there. There are still seats available. You can look at the schedule of courses and register from my website, radius-tech.com. If you go there, the first page, it's all about the training center, and there's a button there to download the schedule and also to register if you want to do that. So pretty much that's all I had. I'm not really here to present on any other topic. I just want everybody to be aware that this new training facility is available, and if you know anybody that's interested in taking authorized NI training courses, I would appreciate if you just spread the word. All right, thanks.
Yeah, thanks, Mark.
Awesome, thank you.
All right. And just so you know, is there any questions or anything?
Yeah, I have a question.
All right.
I took my certification when, there were still proctored exams from NI, and I know it's, you have to set up a webcam now if you do it through NI. So is that one of the benefits of, in-person training and certification?
Yeah, the idea here is that, NI is trying to get back into having these, regional courses is what they're called. Years ago, NI had their own facilities throughout the U.S., but they kind of shut those down. And so they're trying to get back into it in this way by having partners do these services. So the idea is that, you would come to the partner training site for classes and also to take these certification exams. And by the way, if your company has training credits, you can use training credits to pay for certifications and these courses as well. Any other questions? All right. Well, just to let you know, I'm going to have to drop off here pretty quick. I got another meeting that I'm supposed to be at in a few minutes. But again, I do appreciate the opportunity to speak. And if you do need anything, you can get a hold of me fairly readily at radius-tek.com. Thanks a lot.
I think we do have one
I just
question.
have one question. So
Okay.
do we still take the certification exams through you if we don't take your classes?
Yes, that would be a separate thing. So everything is scheduled through actually NI. So if you set up the schedule and you wanted to take it with me, yeah, they would set it all up, and then I would just be there to proctor the exam.
Awesome. Thank you.
All right, thank you.
Josh, were you prepared with? Thanks. I think that would
That'd be preferred.
So you stay,
Yeah.
you know, lock up.
Yeah. Does a bench meter, yes.
Has anybody had any luck with the online proctored exam?
Yes.
I haven't done one in so long because I just recertified.
Yeah, I gave up on it, but like some of the guys on my team that have been like getting their CLDs lately, one of them had to take it 3 times because they kept tearing up, because you're basically VNC'd into a test environment. And so there's like the internet briefly dropped out. And then they couldn't actually see their mouse cursor, so they were just feeling around the screen until they could
Okay.
eventually like cover over something like, oh, I'm over this VI now, okay. Now, so for the last 2 hours of the exam, he had that, so he had to retake it. And then there was like another instance where they had that too. Then one of them, they booked a room in the conference room. And they HR or something did some interviews or something that day and kicked him out. And so then he went into somebody's office that wasn't there. And there was a bunch of like whiteboard writings, completely unrelated stuff. But the person wouldn't let him take it in there because like, he's like, you can't erase this. Like,
Right.
it's somebody else's office.
Yeah.
The VP's like, but they had like all these like concerns about it. So then he had to go get like some big pieces of paper to cover it up. But I'm like, why did they make you go like this and actually show all the stuff that you could be looking at?
Right. I can't remember. Did you proctor when I took? Was it,
I proctored a few, but I
was it Craig?
couldn't tell you.
Digilog
Craig
with
together?
Craig.
Yeah.
Yeah, I did, because I did Digilog with Todd Kutzner.
Yeah.
And stuff.
We might have been in the same, there was a large
You got it
group of
right.
people.
So it was just the 3 of us, me and Todd and Rick Wagner. But he didn't try and take the exam. But they had asked a few times if people wanted to study for it and stuff. I was one of the first early people that took him up on it.
Say like 2015 or something.
It's good news.
Yeah,
So he probably proctored something.
yeah, I think he did.
Saw him last night with Jeff. So
Oh, did you?
little
Nice.
mini reunion. He's with Ansys now.
How's he doing? Good, I assume.
Lots of,
He's married with a kid or two, is he?
yeah, 2 little.
Great. It's been a while since I've seen it, so. No reason to come across it in 2 years.
Good evening. Name is Josh Radesky. I'm with LJB Product Solutions, or both design all down in Muskego. I think from basic engineering, fixture design up to fully automated test cells if you'd like. That's the last of the sales pitch. You can ask me afterwards if you want to know more information. Gonna do a quick rundown of updating a CRIO that's in the field when you're not able to plug directly into it and just update it from the project. So the challenge was there's obviously make programs, changes have to be made, either updates, add new features or fixing bugs. But the program has now been updated, but in the meantime, there are hundreds of systems throughout the world that have the same hardware and need this software update. So most of them, if not all of them, do not have internet access, either in secured areas, either in refinery systems. So saying plug into the internet and download something is not an option. There are lots of hardware platforms. This first system was shipped in early 2010s. Thanks. So the CRIOs are from several generations. They started with the 9073, went to 9066. They're now in the 9056. PCs have changed over that time too. You went from Windows 7 32-bit to Windows 7 64 and then Windows 10. So got to figure out how to handle that. There's data on those CRIOs. You know, they're tracking some preventive maintenance numbers. They've got calibration factors in them. There's important stuff. You can't just lose it. Can't send them a new serial that's been updated and say, just plug that in and use it. The technicians are not computer savvy. Most of them don't carry a computer with them. Some of them don't even carry multimeters with them. So you have to make this pretty simple that just about anybody can use it. And in the event that something isn't right, you need to be able to roll back and put the system exactly back the way it was when you first got there. So that's what I'm trying to address when we got this one. The method that they were using, they do is back at the home base, create update a chassis. So they would have the different chassis available. They would update them, they would install them, they would test them, make sure everything was good. They would then pull an image off of that chassis. Then they would go to the customer site. They did have a custom GUI for a Windows application where you could take that image and deploy it down to the chassis. So great. The problem was you put that image on the chassis, you've lost all of their data that they had before. It is gone. The person doing the update had to manually select the right image. So you don't know what the way that this cabinet is constructed, unless you remove a panel. It's not just opening a door and looking. Unless you remove a panel and look in there, you're not really sure what serial you're even communicating with. So you can run into errors trying to put an image built for a 73 onto a 66. And there was no rollback. This was a permanent thing. So if it went wrong, it went wrong. And now you have a system that don't work. So there were some drawbacks to it, needed some attention. So the new method that we came up with was, I'm going to still stick with the same two first steps. Obviously, you got to test it. So install the software on the chassis, install the software on the PC, test it out, make sure everything is right, pull that image off of the chassis, each one of them. To pull that image off, most of you have heard of replication and deployment utility, or RAD, for the serials. Okay, great. If you haven't, there's a link, otherwise Google replication and deployment utility. When you're pulling an image off, you have some fields that you can put in. You can put in the version number of the image, and you can put a little note in there too of what it is, which fill that out. It really helps. Then it's each one of these data files that are on the serial for these previous versions, I would recreate those with what needs to be changed or updated if there's been new configurations added, or if there are values that we're not concerned with what the value is that they have currently. We want it to be this new one. So basically, like, recreate the config file, delete anything that isn't needed, put in there what we want it to be in there after this update has been completed. So do that for the serials. For the PC, it's kind of the same thing, except here you just build the executable file like you normally would in out of the project. Again, create the configuration files, only including the parameters that you want added or changed. Then created additional EXEs. I was kind of calling these plugins, but they're just additional executables to extend the capabilities of this update. There was a database out there that needed to be modified. Trying to do that is kind of hard. So, or trying to do that within the software so that when they started the software that it would modify this database, it wasn't an option that I wanted to do. So I created a whole separate EXE that would open that database up, perform all the modifications that needed to be done to work with the updated software. And so that would run later on. So yeah, build the actual EXE that you care about, create configuration files, and then these plug-in EXEs if needed.
Is it worth it to try and do a post-build action instead on an EXE or not? Or post-deploy? I don't know if it's.
Well, that's the other thing too, is that I didn't want to do an installer because the way that the file structure had been set up, if I ran an installer, it would overwrite some of the data files there because they'd be included in the installer.
Yeah, right.
So, but yeah, then that one you can do the post-build.
Yeah, I mean,
Post install or EXE or pre-install EXEs. Yeah.
it takes a lot more testing to make sure it's gonna work, and it depends on if you've got a lot of cases to do, that are the same.
Yeah.
That's worth the trouble.
Well, I went this route, like I say, it's computer programming. There's a lot of ways you can get it done. Maybe after this presentation, you can be like, hey, there's this tool that's already out there. I'll go fix it for you. So then I kind of took one from VI Package Manager. I believe all the VI Package Manager files are just compressed. They're just zips with a new extension on them. But I did the same thing. So I organized the files that there's a PC folder with the new application, the configuration files, any additional executables to run, and other files to copy. So if there's brand new files that needed to be added, stick that in the files to copy. Same thing under the CRIO. I'll have my images folder with the images for each one of the chassis and the configuration files that needed to be added or changed. Zip that all up and rename it something other than .zip. Helps to put it with the version. So we're updating to version 10.5.2. 10.5.2 dot update package.
Why do you make it something other than .zip? Is that to get around?
So people don't go extract and look inside. That's really it. Yeah, we're not emailing these out. The best that we had at the time is we would upload the update package to a shared like a OneDrive folder and just share a link. They were getting to the point where they could host something like a service portal, they were calling it. So people could subscribe to that, and when a new update would be published to the portal, an email will go out to notify them that there's a new update available. Here's what's changing. Do you want to download this and go through an update process or not? So it's still technically the machine itself is not tied to the internet, but at least the service technicians out there could be getting some kind of heads up that there is an update available, but they're not there yet. Can't really show you how the application works because that's proprietary, or how the application is written because that's proprietary, but I can kind of tell you the steps. So the first step I did was to update the CRIO. That takes the longest time because you're transferring images. 9073s are pretty quick. They're pretty small image files, and 9056 is a massive image file, especially because you're using the DACMX. So DACMX goes in and out with it. First step, find out what it is. So using the system configuration palette, you can open up a session with your compact RIO. There's some good property nodes in there. One of them is called prod name. That's going to be the chassis number. It'll pop out CRIO-9073, CRIO-9056. So it's really neat to name your image files CRIO-9073, CRIO-9056. That way you know you're deploying the correct image to the correct chassis. There's also property nodes in there for getting the current image info. That's that metadata. What version is it? What notes are in there? So again, imaging a CRIO is a very time consuming compared to every other step that's in here. So if it's the same image rev, prompt the user, do you really want to re-image this? It's going to be the same thing that you had. If they are different versions, then don't bother prompting them. Say, yep, proceed. Be aware of proper error handling out of that one. If those values are empty, that property node will actually return an error. So if there is no version, it won't return an empty string. It will error out on that property node. Back up the existing data files. So they were using FTP. They still are. Technically, that is depreciated, and LabVIEW or NI would like you to go to the web dev. I'll show you there are still ways to get FTP running on a compact RIO, all of them. But that's what we did. FTP in, copy all the data files out. Then pull the image out of the CRIO. Again, we want a rollback feature. So easiest way is to pull the image out. C replication and application, or replication and deployment utility. That is a full-blown project with all the VIs in there for performing most of these steps. Or definitely for the imaging part. Now we're gonna, after that is complete, now we'll push the image that we created, the new updated one, down to the chassis. Only if the current image is different than the updated image, saves some time. On the PC side, we're gonna modify those, we're gonna create copies of what we pulled off. And we're gonna go ahead and apply all of those configuration file changes that we wanted. And then we're gonna copy those files back onto the CRIO. That one's kind of the extensive part that takes anywhere from 15 to 20 minutes, depending on the chassis type. But that step there, really, it's pulling an image off and putting an image down. That takes a long time.
And I think the source code's available for the replication and
Yeah,
deployment.
it's a full project. Yeah, you have, it's well done and good commenting in it. So that's how I did a lot of this stuff, was starting to pull from there.
Is this something where you're updating drivers to newer versions and stuff like that too, or?
Sometimes, yeah, sometimes we were adding new software to the CRIO. So we were going and we would install new software packages that stick with the imaging rather than just copy it down to start.exe and reboot.
Right.
Yeah, that's the driver behind it.
I don't know the capabilities. Have you ever tried using NI package builder?
I haven't.
It's something that you can package together a whole configuration for the PC, including drivers and everything, but I don't know if you can deploy stuff to a CRIO and stuff as part of it or not. I've messed with it some, but I haven't officially used it to deploy to like duplicate a system or something yet.
Has anybody tried that or?
We use Max. So
Yeah.
we can send and receive, we can pull an entire image, all the configuration files and everything with Max. And then I can build it on my machine and copy it over to the target PC or the tech or whoever's plugged into it. And then I can send that real-time image or code back down the whole application in FPGA. And I've kept my configuration files, but I think that might be because, I don't know, I always keep them in the LabVIEW-based bin, wherever it is. I don't know if where's yours are located, but I didn't realize that configuration files would get deleted in that if you weren't pre-imaging.
Which chassis?
What do I got? 9037, 9039s.
Are those running the Linux or are those running the old real time?
Some of them are now on the 21.5 real-time Linux, and some of them are on the older style. What was before that?
Yeah, because I know we were deleting them on the 73s that was running the old stuff. So I just kept the process the same.
Yeah.
I mean, the 9056s and the 66s, I believe, are both
The
running.
9066 and the 9067, I know we've done this with. It's still kind of a weird thing to do because you can break it. It's all based off how somebody clicks things in Max. I'm just curious because it's,
And yeah, Max would work. Like it'd be different if I was able to plug into it and
yeah.
I would go through that, but I'm trying to make it as easy as I could for people who struggle on email.
I hear that.
Are you able to still do everything? Like NI Max, you can do format disk and update firmware. But there's usually only one type of firmware anyway. I don't know what's built into the application image. And do a format.
I don't know that firmware is. I'd have to try that and see if I can update one, pull an image off of it, change the firmware, and redeploy the image and then go back into Max and see what version the firmware is. I would think that that'd be separate, but
I don't know if those update just with each version of LabVIEW or why there'd be a new image. I mean, a new firmware.
Updating the PC is a whole bunch of copy paste. So back up the config files, all the data files that are currently in those folders. I'll back up the existing executable file and then copy paste, copy the new exe in, the files to copy folder, copy all that in. What I did in the files to copy folder is there'd be a hierarchy in there of the folder name where its destination is. Well, that's kind of how the updating tool or the application would know where to put things. Modify the configuration files. Again, only put in there what you need changed or added. And then execute the additional executables using the system exec VI. The command line going in would just be your file path / additional name.exe. And then make sure you do the wait until complete to be true so that it finishes one executable before going on to the next one. In the end, this does work. It's been used a lot. It's been used all over the world. Gone through several different updates of the actual system since then. I believe been about 4 different revisions have been using this. We're about to do another one very shortly. They're testing it now. But the thing was to use this file structure to kind of control how this update process was working. If something is needed, put it in. If it's not needed, don't put it in there. The application that's going through all these steps, basically just looking through folders. What do I do next? What do I do next? What do I do next? There's nothing to do, skip to the next. There is some additional software needed on, or if there is additional drivers needed on the PC side, I include that in the updater application installer. So again, I didn't want to make an installer, a new installer for the actual application I'm trying to update, only because I was worried about it dragging and overwriting existing data files that might be in there. The big takeaway from that is don't put everything in program files data. The way I try to do it now is when you do an installer, those should be your default files. And on the startup, it should be looking somewhere else. If it doesn't see them, copy them from default and put them somewhere else. But that way your new installer package will never overwrite something that already exists. That wasn't the case. So the stuff that's out there, there's no way to work around it. We just always have to be careful never to overwrite stuff that's stored in the C program files, the application, and then data folder.
And then I can't uninstall the stuff on you either. It doesn't know where it's located.
Yeah, it doesn't do that. So yeah, there are extra toolkits. Like I wanted to have I needed the compact CRIO drivers with it. So that was included in this update utility installer. If we needed like SQLite database drivers, those would be included in, or the SQLite libraries, those would be included in that installer and put in the right place. And then with that, when you're installing the package, it can always look to and say, I will only work if the update tool is at this rev level or greater. So you can always see what the rev level is of the application doing the updating and make sure that it's capable. If not, warn them, hey, I can't proceed. You need to update this tool first. The requirements, though, definitely the replication deployment utility. Because yeah, one, I use it to gather the images, and two, it's a great resource for figuring out how to handle a lot of these other steps. You do need the proper software on the CRIO, so there is some extra. There's things that you probably should have on there either way, unless you're really short on space, but I'll show you what those are on another screen. The new ones, the 9056s, any of the CRIOs that support DAC-MX, each one of the modules has a set programming mode. That also does not go down with an image. So there's a gotcha in there. But,
Like whatever it's set to when you pull the image, right?
Nope.
Just doesn't
Unless you tell the
contain it.
chassis what it is, the chassis doesn't care. It's not. So, but it can be done programmatically as part of the real time,
Okay.
the RTVI. So one thing is, it sucks that it doesn't go with the image, but it's really easy to just do anytime the RT thing starts up. For this one to work, the important ones were the system configuration, the WebDAV server, if you are going to be transferring files using WebDAV, or the FTP server, if you're going to be using the FTP. Again, on the system we have, they were using FTP, got to stick with that. On the new ones, like this one here in the compact CRIO 19s, you can't find, if we were to install these, let me stop too, FTP is not in there. In order to get it on, you got to say custom software installation, and you'll see the FTP server as an option to check it, deploy that down. And it prompts you a couple times to say, you really don't want to be using this, but all right. So yeah, use the custom software. And I think this screen is even goofier on newer LabVIEWs. I know I was trying it or doing some stuff with newer, like 2022 or 23, but they don't even have this window anymore. They just have, you want to use this. Like, no, I don't. I want to have more granular control over what goes on it. But I believe there was like little faint text. I mean, what's that rule? If you're supposed to click on it, make it look like a button, and they don't, they make a really faint text that you got to find and then click on it. And you can get to this screen to deploy what you want to deploy. And then programming mode. This is what I'm talking about in Max. You can go in there and you can set the programming mode for every single one of the modules. That, or if you're using your, if you're deploying from your project, that's fine because you have said in your project tree that this module goes to the real time, this module goes to the FPGA. And when you deploy from there, that setting goes down when you deploy. When you're taking the image, that setting does not go down. Yeah, I didn't put it on here, but there is a hot link. I can probably just pop that open. I got access now. So, not the first one to run into this issue. Lots of other people have. They created a knowledge base on it. And they even have this module programming modes.zip with a nice little example VI of how you, again, you use the system configuration tools that are in RT. You can go on there and all the resources, they will say what the programming mode is. I know what it's supposed to be, so I can just have this constant that if you're in slot 1, you should be FPGA. If you're in slot 2, you should be DAC-MX. If you're not equal, change it, save it, move on. Luckily, that does not require a RT reboot. So you can make that change on the fly. It does not require restarting the RT. Just make sure you call the save function after making that change. That's all in that example.
So as long as you change programming mode before you start any of your tasks or something.
Yes, so I put this at the very beginning of that, like my main RT, well before I call the FPGA configuration. But yeah, you want that to happen prior to the FPGA firing up and possibly having errors because the resources aren't available to it.